Okay, so we are starting our first talk in this morning session. The speaker is Professor Tam, who is going to speak about capacity, quasi-local mass, and singular feelings. Okay.
Thank you. So I would like to thank the organizers for inviting me to this nice conference meeting. So this is my second time to Italy. The first time I came is in last century anyway, 1984. I was in Centro for another workshop. So today I would like to talk a little bit about these three kind of concepts. So the first one is capacity for a compact boundary in a asymptotically flat manifold. The other one is some quasi-local mass quantities for some compact set in asymptotically flat manifold. What I would like to say is about the relationship between these two. Are there any things we can say? Well, in doing this, we need some kind of so-called fill-ins. And the metric may not be smooth, so it's singular fill-ins. So this is a joint work. A recent joint work is in fact, is a project in progress with Christos and Mentolidis in MIT. I never met him. So, and another one is Benji Mu from the University of Miami. So we just communicated through emails. Well, I will say something about the background and then about the quasi-local mass, and then we go on to study the singular fill-ins and the application. Finally, we will give, if we have time, we will give some examples to clarify some concepts. So our work is motivated by the proof of Riemannian Penrose inequality, which said the following. Suppose we have a complete asymptotically flat Riemannian manifold so that the scalar curvature is non-negative. So that means in the time symmetric case, in the time symmetric case, that the energy momentum tensor has satisfied certain kind of energy dominant energy conditions. So that means if you look at your place and then you travel in this direction, then when you measure the energy in your frame should be non-negative. So for time symmetric case, that means we have a space-like surface in a space-time, so that the space-like surface is totally geodesic. If this is the case, then that condition is equivalent to non-negative scalar curvature. So let us assume this is non-negative scalar curvature, and then we have a horizon. So the area is A. Then we have this inequality. And the equality holds if and only if mg basically is the Riemannian Schwarz manifold. All right. So let me say a little bit about those concepts. First is asymptotically flat. That means outside compact set, the metric G, we assume it has only one end. So therefore we have only one part going to infinitive is connected. So outside is something like a Euclidean space, and the metric decays like this. So x to the minus tau, the first derivative, we decay one or more, and then second derivative, minus 2 minus tau, etc. That is the decay rate. And the Schwarzschild manifold is just in our setting, I just write in this way. So it's a complete metric, which is conformal to the Euclidean metric with m bigger than 0. So in some case, m less than 0 is also interesting, but in that case, it's not complete. We have to be careful because this part may go to 0. So anyway, we have m bigger than 0, and then we look at this metric. So for this metric is complete, and then x equal to m/2, m over 2 is a horizon. So horizon means that sigma is minimal. We just say that minimal. A fancy, just try to impress people, we just say that this is horizon. Okay, so it's minimal. Well, for this manifold, actually it's just a manifold with two parts. So one is x bigger than m over 2, and the other one is m less than m over 2. So one is near infinitive and other one is near 0. Actually, these two parts are isometric. So if we draw the picture, actually the manifold look like this. So this is infinitive, this is 0, this is x equal to m over 2. So they are isometric. So it's just mirror image to each other. So for an asymptotically flat manifold, we can define the so-called ADM mass, defined in this formula. Well, we can show that this limit exists, and it is well defined if tau is bigger than pi at 1/2. So what does that mean? That means suppose you change coordinates so that it also satisfies this decay condition, and then you computed the quantity. Because you change coordinate, therefore this may not be the same. However, this quantity is the same if tau is bigger than 1/2. If tau is equal to 1/2 or less than or equal to 1/2, then this may not be well defined. So if you use other coordinate, then you end up with other quantity.
So do you need the scalar Gorgias integrable?
Well, integrable, we assume is non-negative, then it's okay, yeah. So otherwise, I think integrable, integrable is not integrable, but if you take a ball or radius r and then take the scalar curvature and then take the limit, if that limit exists, I think that should be okay. Not just L1. L1 is stronger, of course. Yeah. So now next, not the Penrose inequality is not true if we only assume this is minimal. Therefore, we have to assume this is outer minimizing. That means other compact surface, so let us look at this part. Other compact surface inside has bigger area. So if you have another one, so if you have something like that, this is minimal, very minimal, and then you have something like that, and then you still have another minimal surface here. This area may be very big, but the mass cannot be dominate this part. So we have to take this one. So outer minimizing is area. So this was proved by Huskin and Edelman, and then is also proved by Bray. So using different method. So in the proof by Bray, the following fact was used. He used the fact that the ADM mass actually is, it can be considered a weaker conclusion other than the Penrose inequality. So he said that suppose he define the capacity, which has been studied in a previous talk on Tuesday in a very detail. So the capacity defined in this way, then the ADM mass should dominate the capacity. He used this fact to prove the Penrose inequality because he just trying to change the metric, and then he used this fact, and then if you change the metric, then you end up with a certain kind of monotonicity of the metric. And then on the other hand, you have different kind of surface, and the area also of the surface also satisfies certain kind of condition. Then you combine, finally you end up with a very simple manifold, and then you get the Penrose inequality. So we have this one. Well, phi, of course, if we take the harmonic function, so that phi is 1 on the boundary, phi go to 0 at infinitive, then the capacity is nothing but this one. Not in this one. So in this talk, we just say phi is the capacity potential. So let us take a look about the Penrose inequality. So if we have a manifold with boundary sigma, then the Hawking mass is defined in this way. If the mean curvature is 0, therefore this part is 0. If this part is 0, therefore the Hawking mass is nothing but the area, basically. So the Penrose inequality means that the ADM mass will dominate the Hawking mass for under suitable conditions. So therefore in this talk, we would like to discuss between the capacity, the ADM mass, and other kind of quasilocal mass. This is one kind of quasilocal mass. This quasilocal mass is nice, but in many cases it's not positive. It's negative. Usually it's negative. So what is the quasilocal mass we are interested? When I was in high school, I was told that Galileo Galilei dropped 2 balls of the same material with different size from the tower here. So, and then it arrived at the ground at the same time. So people say that this means that the so-called inertial mass and the gravitational mass are exactly the same. So if they are the same, that means you cannot detect the gravitation at a point. Whether you are in acceleration or you're in a gravitational field, you cannot tell. So therefore, there's no energy density for gravitation locally. That means at a point. However, if you are looking at a isolated system, say for example, we forget the outside, then you may get the so-called ADM mass, ADM energy more precisely. And then people trying to understand, suppose we have a bounded region. So what is the energy inside? Can we say something about the energy inside? Then Brown and York introduced this kind of stuff. So they define the Brown-York energy given by this way. So let me explain. So sigma is a boundary of omega, some bounded domain or some domain. So H is just the mean curvature. In our talk, if we are talking outward normal for the sphere, then the mean curvature should be positive. That is our convention. So this is the mean curvature. And then suppose sigma can be embedded in the Euclidean space, then the H0 is just the mean curvature of sigma when it is isometrically embedded in R3. So that is the quantity here. So in Brown and York, so they first look at the variation of the Hilbert, Einstein-Hilbert action. That means the scalar curvature. So when you vary it, so then you end up with a second order differential equation because you have a divergent term. If you have a divergent term, therefore you have integrating by parts, you have a boundary term. If you forget the boundary term, then it's okay. If you take the boundary term, in general, you just prescribe the boundary data. That means the metric, fix the metric on the boundary. But that is not enough because you have to take care of the derivative also. So that is not too nice. Therefore, they introduce another action, which is basically the Hilbert-Einstein action, but with a boundary term. So if you take care of, if you put also on the boundary term, then you use some imitating the classical mechanics, and then you take the derivative of the action with respect to the time t, then you get the negative of the energy. So the energy, when they get, is 1 over a pi minus h integrate over sigma. However, just like the derivative of a function, if you add a constant, the derivative does not change. So your f plus a, take the derivative, is still f pi. So therefore you can pick any so-called ground state. So it's reasonable to say that in the flat space-time, the mass should be 0. So if you do not add this term, or maybe subtract this term, then even in the Euclidean space, so this term is not 0. So now, therefore, we have this kind of stuff. However, as you can see, this may not be defined. First of all, given any compact-oriented surface, there's no way you can always embed it in the Euclidean space. Secondly, if you have embedding, then the embedding may not unique. So if it's not unique, then this is undefined. It's not well defined. So, however, in ours, in most cases, therefore we only, in many cases, we only assume that sigma consists of, maybe disconnected, but consists of spheres, so that it has positive Gaussian curvature. In this case, then this is the embedding exists and is unique by Nuremberg, by theorem. Unique means that if you change by an isometry in R3, then you get the same thing. So, all right. So we get some properties of the Brown-York mass which are related to our discussion. The first property is that suppose omega 3 is a compact manifold with boundary sigma, and omega has non-negative scalar curvature, and we assume that H1, each boundary, each kinetic component has positive Gaussian curvature, so that the mean curvature is also positive. If this is the case, then the Brown-York mass of each component will satisfy this condition. It's not negative. It's not negative. Moreover, if one of them is 0, then omega should be a domain in R3. Well, the second property is that in an asymptotically flat manifold, you take the coordinate sphere. You take the coordinate sphere. You just construct, because for the coordinate sphere, if R is big, then the Gaussian curvature is positive, and the mean curvature is also positive. Therefore, we can talk about the Brown-York mass, and then you take the limit. The limit is just the ADM mass. So therefore, the ADM mass, the Brown-York mass in this sense can be considered as a localized ADM mass in an asymptotically flat manifold. So this properties has been proved by many people, Hawken, etc., many people. But anyway, one can do it in a more rigorous way, mathematically, to obtain this one. So, before I do that, I should say something about this. I still don't know whether, well, if sigma I has positive Gaussian curvature, of course you can always embed. And the mean curvature is always positive in the Euclidean space. However, I don't know whether the assumption that sigma I has positive mean curvature, that means H is positive, whether this is necessary or not. So if H is negative, then intuitively it should be better, but I don't know how to prove it. So of course, if H is 0, minimal, of course, this is true. If H is non-negative, I think that should be true also. So I mean at least for this inequality, not the rigidity result. Okay. So now I will go into the content of our talk. So we consider an asymptotically flat manifold. We have a minimal boundary, and we want to understand the relation between the quantities, the capacity of sigma and two other quantities. So we have an we have an asymptotically flat manifold, all right? So we have a boundary, sigma, maybe call it sigma 0. And then, on the one hand, because the Penrose inequality says something about the ADM mass and the Hawking mass for this one. So I would like to say, to see what is the relation between the capacity and certain kind of quasi-local mass of this part. On the other hand, we know that the ADM mass is bigger than or equal to the capacity by Brace results. And the Brown-York mass for this one also tends to the ADM mass. So therefore, we would also like to see what is the quasi-local mass here related to the capacity. So we have something like that, and we have something like that. So we have two places. So the proof is very the results are very similar. The proof can be unified in some way. So, however, as I mentioned before, usually if you want to define the sigma, the Brown-York mass of sigma, well, sigma may not be embedded, may not be able to embed in R3. Therefore, because of some properties of the Brown-York mass, my co-authors last year, they introduced another concept. So, first, some definition. So, if sigma gamma is a closed orientable surface, maybe disconnected, maybe you have several components, all right? So, we take a compact Riemannian manifold so that the boundary is sigma, and such that G, the metric G, restrict on sigma is just the given metric. Second condition, the first condition. The second condition, omega has non-negative scalar curvature. The third condition, the mean curvature of H, the mean curvature H of sigma is positive. So that is, we don't like this very much, but for the time being, we need this. And then you take the set of all so-called smooth fill-ins. A fill-in is some object like this. So, and then take the supremum. Take the supremum. And this is called the lambda functional. So this may not be defined because we may not be able to find fill-in. So may not be able to find fill-in. But usually, maybe that is not a very serious problem, because we would like to see the boundary of some domain usually. So some remark. If this is a sphere, and then this one is non-empty because you can always embed it in the Euclidean space, and the lambda functional is just this quantity, the mean curvature. So if this is just a topological sphere, and then the first eigenvalue of this operator, where K is the Gaussian curvature, then this is also non-empty by these two guys. So it's always, for me, a hard time to pronounce other people's name. So the point is that they can, if this is satisfied, the second remark, if this kind of satisfied, then they can find sigma here, and then gamma here, and then they can take a long tube enough so that finally this end up with a Schwarzschild metric. And you close it up, that will be a nice fill-in, because the Schwarzschild metric is very nice. Okay. So that's it. The third remark is that suppose sigma is topological sphere. If this one is, the family is non-empty, then this should be finite. This should be finite. So this should be finite. The point is that suppose you have a fill-in, omega, and then the mean curvature is positive, and then sigma is over here, gamma. But we don't know what is the Gaussian curvature of gamma. However, this is compact, therefore the Gaussian curvature should be bounded below by -1, say for example. Then you can always embed this, isometrically embed it into the hyperbolic space. All right. in the hyperbolic space. And in the hyperbolic space, and then we also have certain kind of mean curvature for this embedding. Just like the Brown-York mass relation, we also have this kind of relation, this mean curvature H0 minus H is bigger than or equal to 0 with some weight. What is the weight? Maybe this is the origin of the hyperbolic space. Then the weight is just hyperbolic cosine of the distance to this one. So this is not negative. So if you write down H0, hyperbolic cosine will be bigger than or H, hyperbolic cosine of H. Okay, these two are positive. Therefore, the embedding is unique. Therefore, this function is given. This function is given. Therefore, you can take it out. One side you just take infimum, the other side just take supremum. And this one is fixed, all right? Therefore, finally, this quantity should be bounded by something, right? Something. So one side you just take the supremum, the other side took the infimum. Then you just get, that is the reason why we have finite in this case. So, now, in order to study our problem, because we are working on asymptotically flat, therefore is open to the infinitive. Therefore, we want to close it up. When you close it up, the metric may not be smooth. Therefore, we need to consider the so-called singular fill-in. So we assume that we have an omega g as before. Omega is a smooth manifold. The metric may not be smooth. The metric is smooth away from some compact set, away from the boundary, and then the scalar curvature is not negative away this set, and then P. Well, we need to give some condition on the so-called singular set. We have two kind of singular set. So the first kind of singular set is that P1. This is codimension 1, so this is hypersurface, okay? P2 is codimension larger than 1, so we have two kind of things. So for this one, we need some condition. For that one, in our proof, we also need some condition. So for the first kind, P1 is a embedded surface, so the metric may not be smooth. However, this is our sigma locally, all right? So locally, you just have a metric. So it's smooth here and smooth there, all right? So it's smooth up to here, it's smooth up to there. There may be a jump. So it's continuous but not smooth, right? So if this is T, this T is increasing in this direction. So dt is unit vector pointing in this direction. So this is our sigma. Then we can compute the mean curvature here, and then we can compute the mean curvature over here, also using this direction, the same direction. So we have to assume this is satisfy this kind of inequality. This kind of inequality. The reason that we assume this kind of inequality, because this kind of inequality means that the scalar curvature is non-negative in some sense. So if the metric is smooth, then we can compute, first of all, this is second variational formula. And then we have the Gauss equation, therefore we end up with this one. So this is minus. So if H is decreasing, then R is non-negative. So that is the reason why we need this. For the second one, for the second kind, it has codimension at least L. At least L means that if you take the set, you take the epsilon label of this set, and then compute the area, compute the volume, and then multiply by epsilon to minus L. So if this is finite, then we say that this is codimension L. All right. So we assume that G should be in W1P, where P should satisfy this crazy inequality. But anyway, if L is 2, codimension 2, P is bigger than 6. If codimension 3, that means we are working on point, then P bigger than 3 will be enough. So in the study of this kind of stuff, P2 may consist of disjoint compact sets. Each compact set may have different L, may have different P, but they also all satisfy this kind of stuff. So in our setting, in our proof, we need L is bigger than 3 over 2 if you compute it. We don't know how to handle. Suppose we just assume L is bigger than 1. So L equal to 1, we know how to do it. L bigger than 1, we don't know how to do it unless we know L is bigger than 3 over 2. So what is the condition? So this is 1 point. All right. So the results we get is that suppose sigma and gamma is a compact oriented surface, and suppose we have a singular fill-in satisfy the properties before, then we can find a smooth fill-in. So originally this is singular, then we can smooth it out. So remember the lambda is equal to supremum of the mean curvature for all smooth fill-in. So even this is a singular fill-in, we still have this quantity, this inequality. So how about the rigidity? If the equality holds, then we can conclude that G is flat outside the singular set. And suppose we have a hypersurface. Then on the hypersurface, originally this mean curvature is bigger than that one. Suppose the equality holds, then this should be the same. They should be the same. Well, we would like to see whether this is actually smooth. Because if it is not smooth, then we cannot say too much. If it's smooth, then we have some other kind of conclusion. So how do you know under what condition that for the equality holds, then we have a smooth metric? Suppose the singular set consists of points, then it is smooth. So in their paper, Smith and Yang, in their work, they prove that suppose we have an isolated singularity for a Riemannian metric. This is uniformly equivalent to the Euclidean metric, say, locally. And then, to make it simple, so nearby, the curvature, the rigid curvature is 0, the derivative is 0, etc., etc. Then, you can change the smooth structure so that the metric actually is smooth. So for point singularity, if the curvature behaves well, then we have removed singularity. So I won't talk about the other part because we don't need that. Another one is that suppose we have a hypersurface. Now for equality holds, then they are the same. If they are the same, then it may not be smooth. However, if the second fundamental form are the same, then it's nice. So how do we conclude that the second fundamental form are the same? Well, if the topology is just spheres, each one is sphere, then actually this is second fundamental form is true. So you just take the difference between two second fundamental form. You look at that one is trace free and divergent free, and then because it's a sphere, therefore it should be the same. So that is the idea. All right. Well, if it is smooth, we can say a little bit more. So suppose consists of point or topological spheres, then it's smooth, then sigma. Sigma, originally we don't assume this is connected, but in this case sigma is connected, and omega g topologically is a handle body. It's just like a donut with several holes. And the mean curvature, of course, is positive. So, so our first result say the following. So we apply the following results to the previous result to the following case. So, M is an asymptotically flat manifold, non-negative scalar curvature. We have a compact boundary sigma, and then phi is the capacity potential. So remember, phi is just a harmonic function, so that phi is 1 on sigma. Phi is equal to 0 at infinitive. Suppose on sigma, this condition is true with respect to the outward normal. Then we can find a smooth fill-in for sigma gamma, and we have the following inequality. So let me first say something about the inequality here. So suppose sigma has positive Gaussian curvature. Then, as I said before, this is just 1 over A prime, and then the mean curvature. The first term is just 1 over A prime. If sigma has positive Gaussian curvature, it's just this part. So the right hand side is just what? Just the Brown-York mass. The Brown-York mass. The right hand side is Brown-York mass. Well, you notice that here we do not assume Hg, the original mean curvature, is positive. We do not assume this one is positive. We only assume this one plus that one is positive. Therefore, Hg can be negative, but not too negative. Then we still have this kind of stuff. So if we have this condition, then the left hand side, of course, is positive. Therefore, we still have the Brown-York mass is positive. So this well, about the rigidity. The rigidity said that if the equality holds, because we are working on infinite, just asymptotically flat manifold, our idea is to compactify one point at infinitive. Therefore, the singular point is just 1 point. So if equality holds, then as you can see, we get a smooth thing, smooth metric, and then mg will be conformally equivalent to a handle body. Of course, the metric is beam flat, so inside conformally equivalent to that. In addition, if equality holds and M is simply connected, and sigma has non-positive constant mean curvature, so Hg is non-positive constant, then Mg actually is isometric to the exterior of the horizon, exterior of some coordinate sphere in the Schwarzschild manifold. So it's part of Schwarzschild manifold. If we, in addition, we assume this. Okay. If sigma is a horizon, then we have such kind of stuff, of course, because by maximum principle, this is positive. Suppose sigma is a sphere and this one is bigger than 0, then this one can be embedded as a horizon of an asymptotically flat manifold, etc., etc. So therefore, by the theorem, this is non-empty. Well, in this case, we don't need theorem A. We just do it by hand to know that this one is non-positive. Okay, the last remark I just mentioned before. Okay, so another thing is that Bray and Mill actually they prove that for any connected, suppose M is diffeomorphic to Rn minus omega, and the boundary is connected, then we have this kind of inequality. So if Hg is 0, then this one is bigger than that one. So, okay. Moreover, if equality holds, then this one is isometric to Schwarzschild manifold outside a coordinate sphere. So in our case, we do not assume sigma is connected. They use the fact that sigma is connected because they use the inverse mean curvature flow. As you know, the Huskind element proof for the Penrose inequality. Basically, prove the inequality is true for connected boundary. If it's not connected, then you just choose one of them. Okay. So I don't want to go through the proof. Let me say about something about the result first. If we have time, we'll just sketch. Another one we want to discuss, as I mentioned before, on the one hand, we would like to see what is going on for this quasilocal mass related to the capacity. On the other hand, we would like to see what is going on for a large domain. So going to infinitive, what is the quasilocal mass of this one related to the capacity? So how can we do that? So forget the statement first. So the idea is the following. Suppose we have this kind of domain. Then we just take another copy of the manifold first. Okay? So you just put this manifold to this part. Therefore, you just take the mirror image. So this is original M. We have the M tilde. Okay? You have the M tilde. Well, you have a potential, which is 1 here and still at infinitive. You just take this one, okay? So this will be 0 here and 1 at infinitive. And then you just take another function, I think is 1 plus, call this W. You just take 1 plus W over 2. You take this. Anyway, this behavior is something like 1 at here, but this is not 0. Basically, we don't want 0 here. So phi use in 1 minus phi, defined only in this way. So 1 minus phi look like this is 0 here, and then 1 at infinitive. You just reflect. So it's 0 here, negative 1 here. Okay, if you choose this, call this W, and then take this function. So take this function, then the right hand side will go to 0 in this part. Then you just consider the conformal metric phi 4 times the metric, which is the metric of the original one together with this one. Okay. So for this one, so at infinitive we can close it up. Because we are only interested in this part. Therefore, we just forget this one. Therefore, we have a bounded domain. We have a singular set here. It's nice because it just comes from this part, just like theorem A. And then across this one, this is a hypersurface. Therefore, the mean curvature should satisfy certain kind of condition. So we assume that forget this part first, all right? So we also need certain kind of condition of this part. So under this kind of setup, certain kind of condition here, then we have this inequality using our result on the singular fill-in. Okay? So we need certain kind of condition here. So, So how about rigidity? Suppose the equality holds. So originally, we do not assume, say for example, we may assume sigma, the mean curvature of sigma is positive. To make it simple, okay? Non-negative, okay? Non-negative. Then we can do this. Well, if equality holds, you cannot have a positive mean curvature. This one should be, the mean curvature should be 0. So the mean curvature should be 0 here. If in addition, in this part, if this part consists of sphere, or positive Gaussian curvature and mean curvature, then if equality holds, then mg actually is isometric to part of the Riemannian Schwarzschild manifold. Okay, Schwarzschild manifold. So this is what is sigma C here. Sigma C here is basically is a level set of phi equal to C prime. C prime is related to C. Okay. So if C prime go to, in this case, if C prime go to 0, this one will go to infinitive. And if this one go to infinitive, the left-hand side here will tend to the ADM mass, as I said before. Although this is not exactly the coordinate sphere. However, this is almost like the coordinate sphere, because phi is just like some constant over x plus some higher order term. Okay, so the left-hand side will go to the ADM mass. Then we recover a result of Bray mentioned before. So maybe, I'm sorry, too soon too. Thank you. So, well, if sigma is minimal, on the one hand, by Bray we have this. On the other hand, we also have this inequality for the lambda functional. So can we compare these two? The point is that this cannot be true, because we can always find some example so that the ADM mass is strictly bigger than 1/2 of lambda. Actually, it's much bigger, much bigger. And also we can find example so that the ADM mass is less than 1/2 of this, much less. Therefore, one conclusion cannot imply another one. So maybe I stop here first. All right. So thank you.
Okay, so other questions? Comments?
I was wondering whether in the higher dimensional case one can say something, okay, topological sphere conclusion part apart.
For the non-single field-ins, even though we just write in 3 dimensions, actually is also work for high dimension.
Okay.
One thing I would like to mention is that in 3 dimensions, if we have point singularity, then if the metric is in L infinitive only, we do not assume the W1P. That means the first derivative, we do not assume anything about the first derivative. We still get certain kind of inequality. But in high dimension, it's difficult because we need minimal surface.
Okay.
Minimal surface. So the other part, the point is that in high dimension is even harder to get embedding, because in an over-determined system for the embedding. So.
Okay. And what about does it give hint on how to define Hawking mass in higher dimension?
I think there should be some. I think maybe we can do something. I forget. So in one of my work with Panji Mel, so we try to understand what is the quasi-local quantity and the ADM mass, what is the relations. So we end up with certain kind of quantity. That quantity reduced to Hawking mass in 2 dimensions, but I don't know whether that is a reasonable definition for the Hawking mass in high dimension. But.
Okay, thank you.
Some more questions?
Yeah, another proof of the positive mass theorem uses spinors, so by Witten.
Yeah.
So I was wondering whether you know of any definition of local mass involving the Dirac equation or spinors.
I think there are some other people. There are many approach to study the quasi-local quantity. So I guess there's some some of them. Some of them using spinors, but I don't know because I'm not familiar with that kind of techniques. But
I think it's difficult because sometimes you have these examples where you hide one large black hole in a smaller black hole. And I think for this, and this is very hard to control with spinors. It's much better to control with flows.
I see. Okay.
Okay, so any more questions? Okay, so let's thank the speaker for his nice talk.
thank you. Thank you.
Break.
Lì c'è anche il puntatore.
Sì.
All right, so
Our last speaker is Costante Bellettini from UCL, and he will talk about regularity and compactness for stable CMC hypersurfaces.
Thanks, Andrea. So thanks for the invitation. It's very nice to be back here always. I have vivid memories of taking algebraic geometry in this room. Which clearly made an impression. And I think it's a good occasion to thank the organizers. I think we all enjoyed the conference this week. We all enjoyed the city and the talks. So maybe we can thank Andrea and Luciano. So the talk will be, as you can see, about CMC stable hypersurfaces, and by the end of the talk you will realize that I will have tricked you into a geometric measure theory talk, because the hypersurfaces will be variables at some point. But geometric measure theory, I will keep it looking from the back, not too much in the talk. So we'll let's start from learning how to use this. There we go. So let's start from one of the motivating questions of this project, which is the following very fundamental geometric question. So you consider an arbitrary closed Riemannian manifold, you prescribe a number, and you ask if you can find a CMC closed hypersurface with that value of the mean curvature. So what does CMC means? As the word says, it means that the mean curvature is a parallel vector. So in codimension 1, it's an orientable surface with a constant mean curvature, scalar mean curvature. And variationally, these hypersurfaces arise by fixing an enclosed volume and minimizing the area. So it's a constraint minimization problem for the hypersurface area. As you can see, the first notion is a local notion. You just have constancy that is a local notion, and the second notion seems to be a global notion because you are prescribing an enclosed volume. So we'll come back to this later on. There is no actual discrepancy in this equivalence. One special case of this, of course, is when h is 0, in which case the variational associated problem is the same one, but without prescribing any enclosed volume. So there is no constraint. You just find critical hypersurfaces for the area measure without any further constraint. And they have a special name, of course. These are just minimal hypersurfaces. And you can ask the same question that we have up here in the minimal case. And this has a very long history. It's almost half a century now. And so I'll quickly go through it now before we go back to the CMC case. Dimension 1 case of minimal hypersurfaces, of course, are geodesics. So you're in a surface and you're looking for a closed geodesic. So does there always exist one? If you're in a non-trivial homotopy class, then you can use direct minimization methods, like on the torus. You can fix a non-trivial class and just use the direct method of calculus of variations. You minimize, you find a closed geodesic. If you are in a trivial class instead, as the equator on S2, minimization won't work because you will just get a point, so you don't find the equator itself, which is the obvious geodesic. So you need to devise an alternative method to produce it. And this is what Birkhoff pioneered in his work on closed geodesics, where he implemented a min-max construction to produce them. So let me quickly recall what a min-max is. So basic case, a function in R2 with a saddle point. How do you find the saddle point? Well, you consider two valley points. So A and B are 2 points where the function takes low enough values. You connect A and B in your space in R2 with the green paths. You evaluate the function on those paths. For each path, you find the maximum. And then over the choice of paths, you minimize. So you find the possible maxima, you minimize, you find the so-called min-max value, which corresponds to a critical point. So you produce your critical point in this way. And as you can see, there is, from the critical point, there is a way to lower the value of the functional. You go towards the valleys. And that corresponds to the picture of the equator we had before. So there is a a one parameter deformation that lowers the value of the length. So it's a stationary point of Saddle type. And this is exactly what Birkhoff did to produce geodesics, implement this kind of construction. So how do you do that a bit sloppily? Well, your functional now is the length functional, and you're looking for a closed geodesic, so your space now instead of R2 is the space of closed loops. So R2 is replaced by the space of loops, and the functional is now the length of the loops. So this is a non-negative functional on this space. And again, as you did before, you consider 2 points where the functional has low enough values, so the 2 valley points. In this case, there will be 2 constant loops. You can fix a constant loop at A and a constant loop at B, and then you join them. So you find possible paths that join the constant loop at A to the constant loop at B. So these are what I usually call sweep outs. So these are one parameter families of closed loops that connect A to B. And then, as we did before, you evaluate the functional on these paths. So you consider the length of the loops. So you look for each path, you look for the maximum. And then over the possible maxima that you find, changing the choice of path, you minimize. And this should produce a critical point. So you will find a closed geodesic for your surface. So this is exactly what Birkhoff did, endowing S2 with an arbitrary Riemannian metric. He produced a closed geodesic. Now, the drawback of the approach is that the space of loops is not as easy as R2. So in R2, implicitly, when you do a min-max, you are implicitly using some compactness property because you are taking limits and you're producing a limiting object. Right? So on R2, you just take limits of points that converge to the min-max. Here, you would have to take limit of loops converging to your candidate closed geodesic. And when you consider limit of loops, annoying things can happen in the sense that even a sequence of smooth loops with bounded lengths can produce a possibly very irregular object. So for example, consider this sequence of loops where the horizontal pieces are a construction of the Cantor set, and every time you remove an interval, the middle interval at each step of the construction, you fill in the gap with the red smooth join. So each red curve is a scaling of the original one. So this produces a sequence of smooth loops. The horizontal parts are coming closer and closer together along the sequence. The lengths can be made uniformly bounded. And now let's imagine that we are trying to take a limit of this, whatever it means at this stage. Well, whatever it means, in the limit you can imagine quite intuitively that the blue parts, the Cantor set parts, will come close together, will collapse together in the end. And you can observe, if you try to imagine the Cantor set in the limit, since it's a totally disconnected set, every point of the Cantor set will be such that in no neighborhood of it you will see a smooth object. Right? So whatever point on the Cantor set in the limit you pick, no matter how much you zoom around it, you will always see a mix of Cantor set points and red curves mixed together in a non-smooth way. So these are what I usually call singular points. So a singular point is a point such that there is no neighborhood of it in which the object looks like a smooth submanifold, possibly with some constant multiplicity. And well, the other issue is multiplicity. So the two horizontal parts come together in the limit, and from the point of view of min-max constructions, it's important to take care of the fact that you don't lose mass when you pass to the limit. So the idea of the min-max, again, is that you know where your value should be, because you can just define what is usually called the width, the min-max value. So you know at which level of the functional you are looking for the critical point. But then when you take the limit, you don't want the masses to disappear, otherwise you are at the wrong level for the functional. So you don't want to be any loss of mass. And this is the reason why for min-max constructions, varifolds are the natural answer as opposed to currents. So if you looked at these as oriented objects, which would fit more in the framework of currents, orientations would cancel and the Cantor set would actually disappear in the limit, but you would also lose mass because the Cantor set here you can make it as large as you want. So you can construct a Cantor set of arbitrarily large positive measure and you would be losing mass. So you don't want that, you want to preserve the mass. So in this sense, varifolds that are usually seen as unoriented objects are the natural answer for min-max constructions. Well, this observation that the Cantor set could be as large as you want in measure also tells you that the singular set, that's the collection of singular points in your limiting objects, a priori could be as large as you want. So when you perform these limiting procedures in a space like the space of loops, you have to be aware that these are the two key issues. The singular set can appear and can be huge, and there is a multiplicity that is going to be present very likely. So going back to the Birkhoff construction, it was extended later on by Almgren and Pitts to arbitrary dimensions, and they gave a positive answer to the initial question posed for minimal hypersurfaces. So you're looking for a closed minimal hypersurface in an arbitrary closed Riemannian manifold. So I'll fix n plus 1 for the ambient dimension and n for the hypersurface dimension. So the theorem gives an affirmative answer to that question. So there does exist a minimal hypersurface, closed minimal hypersurface in any given closed Riemannian manifold, which is going to be smooth except for unavoidable singularities that are, however, a very small set. It's a codimension 7 set inside the hypersurface. So Simon's cone, for example, that was mentioned yesterday, provides an example of singularities that can happen, and a priori you can't do anything with that. The proof of this theorem was essentially a min-max a la Birkhoff, but in a more technically advanced framework, because you have to take care of higher dimensions. So this was, as I was mentioning, was carried out in the space of varifolds. So I will come back to definition of varifold later. For the moment, we can just think of varifolds as a generalized notion of hypersurface, which allows what we had in the previous example. So it allows multiplicities, and it allows potentially a lot of singularities. So the strategy of the min-max leads you to a candidate object, which is again a varifold, so potentially an irregular object. And then you would like to say that, okay, now this guy that I got is actually a smooth hypersurface, or it's as close as we can hope to a smooth hypersurface. And that's the role of the regularity and compactness theory, which for this problem was provided in dimensions up to 5 by Shen, Simon, Niao, and in general dimensions by Shen and Simon. So if you're familiar with this proof, the stationary varifold that is obtained here, the candidate varifold, has a good approximation property, where by this I mean the almost minimizing property of the approximating sequence, which allows for so-called stable replacements. Stable minimal hypersurfaces are the object of the compactness and regularity theory of Shen-Simon, and that's how you get in the end that the object you produced is actually smooth, except potentially for a small singular set. So there are these two components in the construction. One is the min-max, which produces the candidate object, and the candidate object is in principle just a varifold, so you don't know any regularity of it a priori. And then you have the regularity compactness part, which then a posteriori proves that the object is actually as smooth as you can hope. This theorem was revisited by Kolding-Dell'Ellis and Dell'Ellis-Tasnadi, same ideas, but in a much more streamlined version. And recently it was revisited in a rather new way that I will describe, with a combination of works by Vikramasekara, Tonegawa Vikramasekara, and Guaracco. So roughly speaking, the idea is that, well, it's again a combination of min-max construction and regularity theorems, but you put the effort somehow more on this side. So you prove a more general result from the point of view of regularity and compactness, and this eases the min-max construction. So as we said before, the min-max a la Birkhoff or Almgren-Pitts has to be performed in a complicated space. That's the space of varifolds. But here, the great advantage is that you can perform the min-max construction in a very nice Hilbert space. That's W12 of the given manifold. So it's super easy space. You can use classical min-max results, like Palais-Mel sequence, or really just the classical tools. But conservation of effort tells you that there's something hidden somewhere else, and that's on the other side. So I will quickly describe how this argument goes. And it goes through the Modica-Mortola or Alencon functional, which is the following. So the reference space is W12 of M, where M is the given closed Riemannian manifold. This is the functional. It's a combination of the Dirichlet type energy and the potential energy. So the potential W is of this type. It's a so-called double well potential with two minima at +1 and -1. So if you are thinking, for example, of minimizing this functional, you can easily see that your function will want to stay mostly either at +1 or at -1. Right? And the role of the first term of the Dirichlet energy is to adjust the transition regions from the +1 phase to the -1 phase. So the parameter epsilon is a small positive number that you ideally want to send to 0. So minimizers or stationary points of this functional will be typically functions that have large regions where they are very close to +1 or very close to -1, and interface regions where you connect the two phases. And the sort of optimal way to connect is to do it along minimal hypersurfaces. So that's roughly the idea. And more formally, what you do is that for every epsilon, you can consider a minimizer or stationary point of this. So the minimizing case was addressed by Modica and Mortola. That's where the name comes from, in terms of gamma convergence. And that's what you do. You have your minimizer or stationary point for the Alencon energy. You consider the level sets of your function. So here you are roughly +1, here you are roughly -1, and then you have the connecting region. You consider these level sets, you give to them a suitable weight. You give a weight in terms of measure, and then you, as epsilon goes to 0, the transition region shrinks, becomes smaller and smaller. It's typically of width epsilon. So as epsilon goes to 0, this is the picture you see. You have more and more constant regions, and in the limit you find the sharp interface where you jump from +1 to -1. And this jump will happen on a minimal hypersurface. So as I said, for sequence of minimizers, this was done by Modica and Mortola, but you can do it more generally just for sequences of critical points of the Alencon functional. So if E epsilon is again the Alencon energy for any positive epsilon, you consider for every epsilon a critical point, and then you send epsilon to 0, and you want to see how to pass to the limit these critical points. So Hutchinson and Tonegawa proved that the weighted level sets of the Alencon critical points will converge in the sense that I just sketched to a stationary varifold. So stationary varifold again is generalized notion of minimal hypersurface. This follows an idea of Tom Ilmanen in the context of mean curvature flow, adapted here to the elliptic version. So you can do this just for critical points, and so Modica-Mortola proved that minimizers converge to area minimizing hypersurfaces. Here you have that critical points of the Alencon converge to critical points of the area functional. And you can do the same also introducing a second order constraint. So if you look at stable critical points of the Alencon, which means that the second variation is non-negative, you converge to stable stationary varifolds. This was proved by Tonegawa and Tonegawa-Vikramasekara, so the stability condition also is inherited in the limit. And I show that the limiting varifold V, using the stability and using the previous work of Vikramasekara that I mentioned before, is not only a varifold, it's actually smooth except for a codimension 7 singular set. So the object that they produce here fits in the regularity theory. That was this more general regularity theory I hinted to before. And then you know that your object is what you hope, is smooth, except for the unavoidable singular set.
But do you need the stability somehow uniform in epsilon? Or
No. And that's okay. So that's allowed. For the varifold theory, you just need the stability with the greater or equal 0. Now there is of course something that we can't hope for. If you are trying to produce a minimal hypersurface by a min-max method, you can't really hope for stability, because the min-max construction does have one direction along which you can decrease the functional. So stability is not really the right thing to look at for that. You should look at index 1. index 1 would mean that except for a one parameter family along which the second variation can be negative, for all the others you have no negative second variation. So that's what Guarraco did. So for every epsilon, he produced a min-max critical point for the Allen-Kahn energy with index 1. And as I said before, this is done entirely at the PD level with standard results on Hilbert spaces. And then he adapted this step to the index 1 case. So what you need to do for that is to extend this regularity result to the case of index 1 limits. And that's actually not very hard. There is a very basic idea that goes back to Smale and Pitts that tells you that if you are index 1, and it works in general for finite index, if you pick two disjoint open sets, you must be stable in at least one of them. Otherwise you would produce two independent families of deformations that give you a negative second variation. So playing with the size of these open sets, actually you're able to show that if you have a sequence of index 1 solutions to the Allen-Kahn's equation, there is potentially one point on the manifold where you lose control of the stability, but other than that, you're fine, you are stable. So all the previous regularity theory applies. And in dimensions 2 or higher, one point turns out to be essentially a removable singularity, so you can, with very soft tools, get rid of that problem. So everything works similarly, and you end up producing a limiting variable that is as smooth as you could hope. Okay, so this concludes the introduction where we've gone through the history of the problem a bit in the minimal case. So we'll soon turn to CMC hypersurfaces again, and well, there is of course one thing we have to discuss. That's the geometric measure theory context of the problem. So we know that ideally we would like now to produce a compactness and regularity theory for CMC varifolds rather than for minimal varifolds under some stability assumption. So that's the project somehow that we'll get to at the end of the talk. And so let me start by saying what the mean curvature is in the class of varifolds. And this is actually the only really GMT thing that one needs to understand to follow here. So let's start from the smooth case. You just take a smooth submanifold. How does the mean curvature arise? Well, essentially it arises by evaluating the first variation of the area functional. So if you can see the deformations of M by any given compactly supported C1 vector field X, so you consider this one parameter family of deformation with initial speed given by X. So at time 0 you're just the identity, and outside the compact set you're not moving anything. So you just move M on this compact set where X is supported, and you evaluate the natural area measure for M. That's the k-dimensional Hausdorff measure here. So you deform M with your one parameter family of diffeomorphisms. You compute the area, and you take the derivative at 0. So you're computing the first variation of area here. And this can just be computed to be this expression here. So you're integrating the intrinsic divergence of M of the vector field, where this is the definition of intrinsic divergence, which is exactly the usual notion of divergence, except that the only vectors along which you take the trace are those tangent to M. So you're not taking the divergence in all directions, but only in the tangent plane to M. So if you're on a smooth submanifold, you can split the vector field in the tangential and normal directions, and compute the two contributions independently. So now X tangential and X orthogonal are independently C1 vector fields, and you can compute that the normal part gives a contribution, and that's where the mean curvature pops out. So you just have a dot product of the mean curvature of M with the given vector field deforming the hypersurface, while the tangential component doesn't really do anything because it's compactly supported. So by the divergence theorem, it amounts to reparametrizing the submanifold. It doesn't change the area. So the contribution actually only comes from here, and so you can rewrite the previous formula in this form. So the first variation of area for these deformations is essentially encoded in the mean curvature. So now we want to look at these two terms, which are equal, but actually they are morally extremely different. Not in the sense that they're not equal, but just in the intrinsic sense. So if you look at this one, you are speaking of mean curvature, so you do need to know that M is a C2 submanifold. Otherwise, you don't know what to say, what H is. But if you look at this one here, you don't need that much to write it down. So the divergence, as I said before, is computed once you know the tangent at the point to the submanifold. So that's already only a C1 notion. You just need to know who the tangent to M is. So for this you need C2, right? For this you need C2.
For the first computation?
For the first computation you need C2.
Even for the first one?
For this you need C1.
Okay.
Yeah. So that's the point. For this you just need C1. And actually you need less. So for this you would need C1 because you want to know what the divergence is and you need the tangent. But you're integrating it. So you just need to know that the tangent exists almost everywhere. And that's exactly what you like if you are thinking of a geometric measure theory framework, because all you need to know is that there exists a tangent plane almost everywhere. And then immediately you remember rectifiable sets. So this only requires the tangent to exist almost everywhere, and that's exactly what rectifiable sets are. So a rectifiable set is a set that is given by a countable union of Lipschitz pieces and another set of measure 0. So that's the typical object that you use in geometric measure theory to replace the notion of submanifold. And that's exactly what allows you to write down this term. Because rectifiable sets have the good property that the tangent plane is well defined almost everywhere. So actually this is an equivalent characterization to the one I just said. So being a countable union of Lipschitz submanifolds plus a zero measure set is equivalent to requiring that there is a well-defined notion of tangent almost everywhere. So if M is not a C2 submanifold but merely a K-rectifiable set, actually this makes sense. So you can do the first computation just with that. And so the typical idea at this stage is that the equality here that was essentially a theorem before, you can now use it as a definition of mean curvature. That's exactly what you do when you introduce weak derivatives. You say that something is the weak derivative of a function if the integration by parts theorem works. And whatever you put on the right hand side, you call it weak derivative. And depending on where that weak derivative lives, you have different classes of functions. So a function will be an W1P function if the weak derivative is an LP function. It will be BV if the weak derivative is a Radon measure, and so on. And you can do the same for in this framework. Depending on what the H is, you have different classes of varifolds. Yeah, so a varifold now, from now on, an integral varifold will be simply a rectifiable set. So that's the object we just introduced. And we have to remember that we have to allow also an integer multiplicity on it. So if you remember the example I gave in the beginning, multiplicities can arise and you have to keep track of them. So you consider a rectifiable set. So almost everywhere there is a good notion of tangent plane. You allow an integer valued multiplicity on this set. And you define the generalized mean curvature by saying that the mean curvature is whatever makes this formula work.
But should there something embedded in a manifold, or is it some abstract notion for abstract manifold?
Typically you embed it in a manifold, yeah.
And it is essential, right? Multiplicity is
M. Yeah. That's a different class of varifolds. You can allow that, but that would not be an integral varifold. That would be a more general rectifiable varifold. So for the purposes of what we have here, this is all we need. So you just need integral varifolds, which amounts exactly to requiring the n there. So as I was saying before, depending on where the mean curvature lives, you have different classes of varifolds, and for a decent starting theory, you need to require that the mean curvature is in LP log for some p greater than the dimension that you're looking at. So if the object is n-dimensional, a good idea is to look at the class of varifolds whose mean curvature lives in LP log. So this is the natural measure associated to the varifold, that is the Hausdorff measure weighted with the theta that you've prescribed. So that's the natural area notion on on the varifold. So if this assumption is not made, you could have sort of pathological situations that we want to avoid. And the other important thing that tells you that this is a good class of varifolds to look at is that there is some sort of initial regularity that you can assume, and that's given by Allard's theorem, and some initial compactness that you can assume, again given by Allard's theorem. That's what I'm saying next. So if you consider an integral varifold with mean curvature in LP log for p greater than n, then there exists a C1 part, which is an open dense set of the whole varifold. So there is an open dense subset of the support of the varifold where this a priori very regular object is actually supported on a C1 alpha, on locally C1 alpha pieces. So the open dense set could be very small in measure, so you have no control on the fact that you have a large regular set. The regular set a priori could be very small, but it's non-empty and it's open dense. And it's of C1 alpha type. Moreover, you have a monotonicity type formula for the area, just like you do for minimal surfaces. So this ratio here, you are comparing the area of the varifold in the ball of radius rho around an arbitrary point y. You are comparing it to the area of the corresponding disk of the same radius. So you fix any ball around y, you look at the area of the varifold inside that ball, and you compare it to the area of the flat disk inside that same ball. So this ratio turns out to be actually almost monotone in rho. As rho goes to 0, it's non-increasing. So there exists in particular a limit at every point y, which is called the density of the varifold at y. Almost everywhere it agrees with the little theta you prescribed in the beginning, but it's actually defined everywhere. So somehow it's a good representative of the multiplicity, and it's well defined everywhere. Yeah, so this ratio is almost monotone as rho goes to 0. There is an error term. So if the mean curvature is 0, it's exactly monotone. Since this mean curvature is non-zero, it's just LP, you have an error term that vanishes as you go to 0. So in particular, you still have a well-defined limit, which is the density, and it agrees almost everywhere with the one you prescribed in the beginning. It's an integer almost everywhere. So for example, if you think of the Simon's cone, you have a density at the origin, but that's not an integer. So almost everywhere it's an integer, but it is defined everywhere, but not necessarily an integer everywhere. And moreover, this density tells you that in order to have a singular point, you need high multiplicity. So if you have multiplicity 1 or slightly higher, so there is an epsilon regularity result, if the multiplicity is bounded by 1 plus epsilon naught, where epsilon naught is some universal small constant, then you are in the regular set, you are in the C1 alpha set. So in order to have bad singularities, the multiplicity must be high. So Allard's theorem is a varifold analog of this PD theorem. If you have a solution to the Poisson equation with f LP with p greater than n, and then is the dimension of the domain, then the solution is C1 alpha, and alpha is 1 minus n over p, and that's exactly the regularity that you have in Allard's result. And the other aspect of Allard's theorem is that it gives you some compactness. So if you are in this class of varifolds and you have LP bounds on the mean curvature and the uniform bounds on the mass, you can always subsequently extract converging varifolds, converging to a varifold in the same class. So there is some initial information on the regularity and on the compactness that you can assume thanks to Allard's result. Okay, so now let's switch to CMC. And so the idea, of course, would be to say what it means for a varifold to be CMC unstable now. So let's start again from the smooth case. If you have an oriented C2 hypersurface, you can define, of course, you can define the area as the Hausdorff measure, and you can define the enclosed volume in this way. So this expression here, if M is the boundary of a domain omega, by the divergence theorem, you can compute it's exactly the enclosed volume in the usual sense. So X is the radial vector field. So by the divergence theorem, if M is a boundary, this is exactly the volume enclosed by M. But this expression doesn't require you to know that you are enclosing a volume. So you can use this even when you don't know that. And this basically answers the issue we had in the beginning. So the notion of being CMC is actually local because you can make sense of this also locally. So you can speak of volume preserving deformations even locally, even if you don't actually know that you are enclosing a volume.
So it should be the volume of M of the volume of...
So by this I mean volume enclosed by M.
Volume enclosed by M.
Yeah. So this is the area measure of M, and this is the volume enclosed by M.
So why you're saying that you can preserve the volume even with local perturbations?
Right, so you can prescribe, you can constrain your deformation to conserve this quantity. And so you can have a local vector field on a portion of M.
So in some sense you're saying that it is easier to control the constancy of that quantity when you make a perturbation. So you can use the explicit...
This makes sense much more generally, right? You don't need to do a global deformation, you can do it just locally.
Ah, okay.
So that's the advantage.
You can modify this in another part, even if you're dealing with some size part.
Yeah, so you can, the advantage is that you can localize everything. You don't... So this is okay for C2, and for C2 you have the following classical facts. So being CMC, being constant mean curvature, is equivalent to being stationary for the area with respect to ambient deformation that preserved the enclosed volume, and as we just said, this is now really just a local notion. And it's also equivalent to being stationary for this functional here, where you put the mean curvature in as a Lagrange multiplier, and you have the area plus H naught enclosed volume. So these three are all equivalent formulations. They all amount to being classically CMC C2. The important thing for our purposes is that B and C actually make sense for C1 alpha embedded. So if you are a C1 alpha embedded hypersurface, locally you are a C1 alpha graph in some coordinates. So you can make sense of notions B and C locally, as we said before, for this C1 alpha graph. And then what you get is a PD. So by writing down the stationarity condition in either of these two ways, if you are C2, you would get this PD. And if you are C1 alpha, you get the weak formulation of this PD. And by weak form, I just mean that you integrate by part and you move the divergence on the test function. And then you are in a relatively classical situation. So you have a PD with a C1 alpha solution. You can bootstrap to C2 and higher. And then you get that once again you are in a classical CMC case, smooth CMC. And the fact that this makes sense for C1 alpha is important because, as I said before, when you have a varifold, C1 alpha is something that you know, thanks to Allard's theorem, you can expect at least somewhere. And so for those parts of the varifold, it makes sense to prescribe conditions like this. And that's also why it's important to do this only locally, because otherwise you wouldn't know what to do. So this is the condition we will impose on the varifold later on. For the C1 alpha part that we know is non-empty by Allard's theorem, we will impose either of these two conditions. So this will mean for us that it's CMC. So let's move on to stability. Now we consider a smooth CMC hypersurface, and we want to impose that the second variation is non-negative for all volume preserving deformations. So as we saw also yesterday, this amounts to an inequality of this type. This is usually called the weak stability inequality, where weak refers to the fact that the test function zeta has to satisfy this constraint, which is related to the volume preserving property. So stability for a C2 CMC hypersurface amounts to this, and it makes perfect sense also if you're just immersed. So you can just be immersed CMC, you can still make sense of this, either of the inequality by pulling back on the abstract hypersurface, or you can simply make sense of the notion of enclosed volume also as an immersion. Okay, so as you can see, I haven't really said anything about things that are not classical here. I've said what stationary means and what stable means basically only in classical setting. And basically, I will never answer the question of what it means for varifolds because we don't need it. So that's the approach we have for our regularity theory. We are only going to impose these conditions on parts where they make sense classically. So C1 alpha for the stationary part. Then thanks to the elliptic bootstrapping, you get C2. And then on the C2 immersed part, we will impose stability. So before we get to the theorem, I need to introduce some terminology. So the spirit of the result is to obtain a regularity theorem for CMC stable varifolds, whose conclusion is that the object is actually smoothed away from a codimension 7 singular set. So just like in the minimal case, that's the ideal. So we need to make some assumptions, so they will be of two types. One is on this type of singularities, so this we call classical singularities. We say that P is a classical singularity. If locally around P you have a situation where the support of the varifold is given by a union of 3 or more C1 alpha hypersurfaces with a common boundary that meet at the common boundary. So pictures like this. So these are called classical singularities, and the assumption of the theorem will be to assume that these don't exist. So the reason for that is, as I said, we want a theory which leads to smoothness. And I mean, if you allow this, of course, you're not getting smoothness because there is a codimension 1 singular set here. So these are ruled out by assumption. And it's the sort of things that, for example, is present also in the minimal hypersurface theory and is very easily checkable in the Allen-Kahn approach I described before. And the second type of structural condition is for what we call the twofold touching singularities, which means the following. So P is a twofold touching singularity. If locally around P, the support of the varifold is given by the union of exactly two C1 alpha graphs that touch tangentially, okay, at the point P. So what's the role of these singularities here? So the role of this can be appreciated if you again think in terms of what you want to get. So we want a regularity theory together with a compactness theory. So these usually go together. When you have a regularity result, you also want an associated compactness result because you want some flexibility in the applications that allow you to say that, okay, if I have this class of objects and I take a limit, I'm in the same class at the limit. So usually the difficulty of such theory is to find a balance between enough assumptions that allow you to conclude some regularity and mild enough assumptions that allow you to conclude a compactness result as well. So if you think in terms of the compactness you might want to get, you can understand that these touching singularities have to be taken care of. So if you just start from a local situation where your CMC hypersurface is a union of two half cylinders like this, so these are smooth and stable as well because they are separately graphs, and then you let them just come together, you see that they can come together along an n-1 dimensional submanifold, and this is a touching singularity, for example, of the type I said before. And it's a rather large touching set. It's a codimension 1 in the hypersurface. So if you want a full compactness result, you have to allow this touching set to be at least this large. Right? And if you're familiar with the Shen-Simon theory, you remember that the prescription there is that the singular set is codimension 2. Which would not allow for this. So if you want a full compactness result, you have to somehow relax that assumption. So this is for the compactness. You want to allow such touching singularities to happen on potentially a large set, at least of positive n-1 measure. At the same time, if you now think of the regularity aspect of the matter, well, one of the key things about codimension 1 problems when you do regularity theory is the following fact. So if you know that your, say, varifold is flat, so it's close to a hyperplane in distance and it's close in mass to a multiple of the hyperplane. So you're close, say, to 3 times a hyperplane or 2 times a hyperplane. Then you want to conclude that actually your object is a sum of graphs, separate graphs. So that's what you do in the minimal case. And this is the great divide between codimension 1 problems and higher codimension problems. So in higher codimension, forget about this. If you're flat, you're not going to be a sum of graphs. But in codimension 1, that's actually the key to the higher regularity that you have. So if you're minimal, once you have C1 alpha minimal graphs, then they can't touch by the maximum principle. So they are individually C1 alpha minimal, not just globally. And so you can just use elliptic theory to bootstrap to C2. Okay? So C1 alpha is a natural thing to hope for if you are trying to do this regularity proof by the Giorgi type argument. So these are usually obtained by the Giorgi decay argument, which leads you naturally to C1 alpha. So if you know that you have C1 alpha minimal graphs, by the maximum principle they will not touch, so individually they solve the PDE, which is the same as that with h equals 0. And so you just bootstrap, they're separately C2 and you're done. But in the CMC case, this changes, of course, because CMC graphs can touch, right? You can think of two sphere caps touching or two cylinders touching. So if you are in a situation where you have used the Giorgi decay tools to get a C1 alpha collection of graphs, and the object is globally known to be CMC, there is no immediate way to say that separately the graphs are going to be CMC and smooth, okay? Because the touching prevents you from extending the PDE. So we said before that you must allow at least a positive n minus 1 dimensional set of touching, and that's too large to extend the PDE by standard cutoff arguments. And also for the stability, actually, you have the same problem. So the Shen-Simon approach with a codimension to singular set was working because stability can be extended across that set by capacity arguments. But with such a larger touching set, you can't do it. So you have to devise different ways to do that. And so, yeah, as I was saying, you can't conclude that each graph is separately CMC, so you can't use individually for each of them the PDE. So you have to do something else. And this is actually not just a technical issue. So unless you make some further assumption, this can just fail, that you have separately smooth CMC graphs. So just think of this example here. So here you see you have two graphs. So this part is counted 2 times. So the two graphs coincide on the right. So if you look at this picture now, this is clearly a singular point, and the rest is smooth embedded. Okay, these are arcs of a circle with the same radius. So the embedded part of the object is CMC in the usual sense, and it's also stable in the usual sense because they're separately graphs. So if you were to impose the conditions of stationarity and stability classically, that means away from the singular point, because for the embedded part you would impose stationarity, and as I said before, for the C2 immersed part you want to impose the stability, you would be imposing it only on these 3 arcs separately, so they're satisfied. But now you are in a situation where you have 2 C1 alpha graphs, but the bottom one is just C11. The bottom one changes the sign of the mean curvature when you go from left to right. So the issue of wanting to upgrade your result from C1 alpha graphs to C2 graphs individually satisfying the equation fails here. And the reason why it fails is that the key quantity for that is still to have a control on the size of the set where the graphs can touch. And here the size of the set where the 2 graphs touch is positive n dimensional. They touch on half of the picture. So you have to find a balance. As we said, we need a large enough touching set to allow compactness, but not too large, otherwise you can't get all the smoothness that you want. So what we concluded is that, so this is the final theorem, the right assumption will be assumption B here. So let's start from the beginning. This is a joint work with Neshan Vikramasekara. We have an integral n varifold, so the class I introduced before, with mean curvature in LP for p greater than the dimension. As I said, we assume that there are no classical singularities, so these 3 C1 alpha hypersurfaces coming together, 3 or more coming together, are ruled out by assumption. And this is the assumption on the touching singularities. So we prescribe that whenever you have a touching singularity, the measure of the set where the 2 graphs touch has to be 0 HN measure. Okay, so this is between the 2 pictures we've seen before. In the case of the 2 cylinders coming together, we saw we had to allow positive HN-1 measure to allow for compactness, and we saw that if you have positive HN measure, the regularity becomes very problematic. You can't get smoothness. So this is the intermediate assumption. We prescribe that the touching set has 0 HN measure. And then we impose the variational hypothesis we discussed before. So on the C1 alpha embedded part that is non-empty by Allard's theorem, you prescribe stationarity in the variational sense, either with the Lagrange multiplier or without, with volume preserving variations. On the C1 alpha part, this leads you to the PDE, which allows you immediately to say that the C1 alpha part is actually C2. And then you want to impose stability on the C2 immersed part. So now you know that there is a C2 part. You consider any part that is C2 immersed and you prescribe stability there. So this is how we impose the stationarity and stability conditions on the varifold. So they are imposed wherever they make sense in classical terms. So there is an observation here. So for D, where we are prescribing stability on the immersed part, we are looking essentially at a situation like this. These are C2 graphs touching. Okay? They can't cross by assumption 1 because there are no classical singularities. And the set of touching is of n-dimensional measure 0 by assumption B. We also know that the embedded parts are CMC in the classical way, so you can conclude just from ABC that you are in this situation with the mean curvature that is constant on all the embedded parts. At the same time, these are assumed to be C2 in D, so you know that the whole picture is made of two C2 graphs. So the mean curvature has to be continuous in particular, and you know that it's constant except on a set of measure 0, so actually it's constant everywhere. So this tells you that whenever you look at this object, the C2 immersed part of the support, by A, B, and C, you are looking at classically CMC immersed. Okay? Because as I said, the mean curvature has to be constant if you put together all the previous assumptions. So you're looking at the CMC immersed hypersurface, and as we said before, you can just impose the stability on that in the classical sense, so as a stability as an immersion. So the conclusions of all this is that it's as good as it gets. There is an actual singular set of codimension 7, away from which you are either classically CMC embedded, or you are locally made of two CMC pieces touching tangentially. And they touch tangentially a posteriori on an n-1 submanifold at the most. So let me comment a bit on the, again on assumption B. Another reason, in addition to what I described before, for this assumption is that it fits well with Cacciopoli sets. So if your varifold actually comes from endowing the boundary of a Cacciopoli set with multiplicity 1, so you consider the multiplicity 1 varifold associated to a boundary of a set of finite perimeter, then assumption B turns out to be automatically satisfied. It's a relatively easy consequence of the Giorgi's rectifiability theorem. So another potential application of the theory would be to look at problems in capillarity theory, and upon extending this theory, you can imagine that Cacciopoli sets are a natural class of objects to look at. And so the role of the structural assumption is that you would like them to be easily checkable in the application. So, I mean, in the assumption 1 has been shown to be easily checkable already in the Allen-Kahn context. Assumption B is easily checkable in the Cacciopoli set context. So this is a bit the spirit of the assumption. So as opposed to other varifold results where you prescribe the size of the singular set, for example, that's the Schoen-Simon approach, and that can be hard to check. Here the spirit is to find structural conditions on the varifold that are somehow easy to check in the applications. So I already discussed this. So just let me remark on the stability assumption again. So this is the same picture we have there. So what we are allowing when I say that we are assuming stability of the C2 immersed part as an immersion, we are allowing this. Okay, so if you know already that you're locally in a part where the varifold is a C2 CMC immersed hypersurface, then you're allowing these deformations. But if you know only that the sheets are C1 alpha but not C2, then you're not allowed to move away the touching points. Then you can only deform like this, but you can't move the touching points. And then, of course, we have the associated compactness result, without which the theory wouldn't be very useful. And it's just what you expect. So you have a sequence of integral varifolds satisfying all the assumptions that we had in the previous theorems. the natural bounds are a bound on the masses, uniform bound on the masses, and a uniform bound on the mean curvatures. You can just take it in absolute value because a posteriori by the regularity you know that they are, after all, classical CMC, so you just prescribe a bound on the modulus of the mean curvature. And then the limiting object is a varifold in the same class, and so a posteriori also as regular as it gets. So to conclude, the convergence is the weak convergence of varifolds, which is the measured theoretic convergence. To conclude, let me just point out that this version of the compactness, we've slightly refined it in a joint work with Vikram Sekar and Otis Chodosh by also obtaining a priori estimates of the Shen-Simon-Yau type in low dimensions. So in dimensions up to 6, that's when things are completely smooth. If you assume that you have a smooth immersed hypersurface with constant mean curvature with scale invariant bounds on the mass and on the mean curvature, and the object is of the type we described, so it's either embedded, or if it's not embedded, it's two CMC guys touching tangentially, then we get a priori estimates on the second fundamental form, scale invariant estimates again. And this is done under weak stability, so it's the analogous result to the Shen-Simon-Yau result, which holds under strong stability. The weak stability means that it's for volume preserving deformations. So in terms of the inequality, the weak stability inequality looks exactly the same as the strong one, but you are prescribing the test function to have zero average. So it's a weaker notion. So this will fail in higher dimensions unless you assume something else. So if you also assume that your varifold now you're in general dimension, but it's flat in some suitable sense, then you conclude that it's again a sum of graphs, and you have again a bound on a C2 bound like this. So I'll stop here, and thank you.
So you said your varifolds are always unoriented, but I'm wondering if you want to define mean curvature, you always need an orientation because it has to point
so this
in a
is
certain direction.
a very good question.
And also, if you have an orientation, you could avoid this double touching because they go in different directions. Why don't you use something oriented?
So there is a version of a corollary of the theorem that holds for Cacciopoli sets, and so in that case you do have an orientation. The thing is that the effort for proving it is exactly the same as for proving this one. So yeah, you can do it, but we didn't find any shortcuts for the proof. So yeah, and so essentially that is the answer. But yeah, it's true. And in fact, in the assumption on the stationarity, to formulate it correctly, you have to formulate it in terms of the fact that any orientable piece that is C1 alpha satisfies the stationarity condition. So you don't know any global orientability, and you prescribe that whenever you have a piece that is C1 alpha and orientable, it is a stationary point for the function.
And at the beginning you mentioned some theorems about the existence of minimal surfaces. Do you also have similar theorems for constant mean curvature?
So this is what we are aiming to do next. So we would like to implement this regularity theory in an Allen-Kahn approach for the proof of existence of CMC. So there is a paper from last year by Zhu and Zhu asserting the existence of CMC hypersurfaces in dimensions up to 7. Using the Almgren-Pitts approach, so min-max a la Almgren-Pitts. And so I can't say that I've understood the proof, but if I understand it correctly, our result also gives you the result in all dimensions, our compactness result. But we would like to do it using the Allen-Kahn, so using this different approach.
So it's not clear whether this minimal surface can be perturbed to constant mean curvature surfaces.
So for small mean curvature, the existence is known as with perturbation techniques. So either very high or very small mean curvature, you have existence result by either perturbing minimal or by perturbing small geodetic balls. But for all intermediate values, it's harder. Yeah.
I have first a very minor curiosity. So you define in your theorem, so maybe we can go back there so it is easier. You define the function u1 and u2 to define exactly that the hn measure is 0. So in the case of Cacciopoli sets, who are u1 and u2?
So if you're thinking of a Cacciopoli set that is made of two domains touching, so if you have the boundary of this, but here you have a very regular touching potentially. So they're not really coinciding the boundaries. You might have a very regular touching.
Yes.
So now if you consider the boundary of this set, for sure you can have a nice situation like this. So u1 and u2 are these two. But a priori you might have a very complicated situation, but as a consequence of the Giorgi's rectifiability theorem, you can conclude that if you're in a situation where the boundaries are C1 alpha, so this is why it becomes easier to check the assumptions, because we are assuming that a touching singularity is made of two C1 alpha graphs touching.
So in this case, u1 and u2 are the local defining functions?
And they're the locally defining functions for the boundary.
Okay.
So the Giorgi's theorem then tells you that it's of measure 0, the touching set.
And you have this function also in the general case of variables, you can construct this. So I have another curiosity. When is there any general class of examples, so the more general, that provide you this list of property that holds? So many cases.
All the properties listed here?
Yes, concrete situation for.
The most concrete one I can think of are Cacciopoli sets.
Cacciopoli sets.
Yeah.
Where all these properties are automatic.
They're not automatic, but they're automatic in the typical applications.
Okay.
So, for example, there is a corollary of this also more suited to the class of Cacciopoli set. So, as I mentioned before, if you are prescribing stability as an immersion, you would need to perturb this by changing it like this. So, if you are in a context where you are working only with Cacciopoli sets, this becomes undesirable because you destroy the fact that you are a boundary of a Cacciopoli set in doing this. So we have a parallel result that is more suited only to Cacciopoli sets, where basically you assume stationarity in a slightly stronger sense. So you assume stationarity by making deformation of the Cacciopoli set in the class of Cacciopoli sets with respect to the L1 topology on Cacciopoli set, which is slightly stronger here. It's only assumed on the embedded part, but in that case you could deform it in a wider class. But that allows you to basically remove all the rest. You remove everything up here. It becomes all automatically satisfied. And you need to require stability only on the embedded part then. So you get rid of this problem if for some reason in the application you know that you can't do this.
Thank you.
So the mean curvature is the sum of the two principal curvatures. I was wondering if you study problems
in 2D, you mean?
In say 2D, so 3D ambient.
Yeah.
If you replace the mean curvature by maybe a mild nonlinear function of the principal curvatures, so can you still?
We never thought about that. So you want to, for example, you want to consider LP versions of the mean curvature, or?
For example, anything which is maybe.
We never thought about that because there is not necessarily an immediate variational meaning. So that's the reason why we haven't thought about that yet. But if there is a variational meaning, as it happens in some cases, I can imagine that at least part of the theory can be reproduced. So one important aspect is that if you compare these to the result for minimal cases that was proved by Neshan, the assumption of stationarity was given by saying that the generalized mean curvature is 0 everywhere. So what we realized is that actually you can, so if you see all the assumptions here are made on pieces of the variables. It seems that there is no global assumption. So it's a bit strange in the sense that it feels like you're putting assumptions on random scattered pieces of the variables and then you get something smooth. And in fact, the only thing that patches things together is this assumption here. So the fact that the mean curvature on the whole variable is in LP is a global assumption, and it's the only global assumption. And the first part of the proof is actually very robust. Under only this assumption, you do the Giorgi decay estimates, which lead you to the first step of C1 alpha regularity. So yeah, if you have assumption that come from variational problems and they give you enough control on the mean curvature, or on potentially on functions of the mean curvature, it's possible that you can still implement at least the first part of the proof and get some initial regularity of C1 alpha type.
So how essential is your assumption that you're in Euclidean space? Can you also do it in
in work in preparation, we're actually extending this result to Riemannian ambient manifold, which just requires you to carry over some errors. But actually, we're extending this to prescribed mean curvature. So on a Riemannian manifold, you can prescribe a positive function, and you look at variables whose mean curvature at every point is the value of the function that you've prescribed at that point.
Function on the manifold.
Right, so you put a positive smooth function on a manifold and you look at variable whose mean curvature attains the values. So the extension to the Riemannian case is not written in the preprint because it becomes a sort of an extra intermediate step. We are just going to do straight away this more general case.
You are expected to show that there exists a mathematical
For the existence theory, that's the hope, yeah. So we'll see. For the regularity, I'm sure that the extension works.
Get there sooner or later.
So about the assumption, integrability assumption on the mean curvature. So you mentioned the parallel with the Poisson equation, but in fact in the Poisson equation, the sharp hypothesis to get C1 regularity is something slightly. I mean, it's a Lorentz space assumption on the right hand side. Do you think that here it could work? I mean, to get C1 regularity?
It could, but I mean, I don't know if the game is worth the result. I mean, I wouldn't know of any application at the moment where you can use that class of variables instead of this.
Mm-hmm. Yeah, of course.
So, given the amount of technicalities involved, you would need a lot of patience if you want to write
just
it down.
Just curiosity. Yeah, of course.
All right, so if there are no further questions, we can thank Costante again. I also take the opportunity to thank everybody, both speakers and participants, for attending. Okay, thanks.